All right, so in the past we've talked about describing scatter plots, using residual plots to assess whether a linear model is appropriate. We've talked about finding the least squares regression line if it is appropriate. We've talked about strength and correlation. However, we're using our model to make predictions. So the next obvious question should be, whenever we make a prediction, how good are these predictions when we're using our linear model? So there's kind of two ways to measure how good our predictions are. And the first one we're going to talk about is the standard deviation of the residuals, denoted S. Here's the formula for calculating it. Let me just remind you a couple things here. If we have a least squares regression line about some data points like this, when we make a prediction, when I pick a certain value of x, let's say I pick this value of x right here, this is the actual value of y, and then this is my predicted value of y. So there's a difference between those two things. That's my error. That's called the residual. So the question then would become, when I make these predictions, on average, what are my predicted errors, or my prediction errors? What are the errors in my predictions? So we could average these out, kind of. But we kind of run into the same problem that we talk about whenever we're talking about the average distance from the mean. Namely, this is a positive difference. This is a negative difference. So they're going to kind of all cancel each other out. So what we do is we square those values, just like we do when we're calculating the standard deviation. It also penalizes points that are further from our prediction. So we talked about those. So basically we take these residuals and we square them to make them all positive. And then we're going to average them out. So we divide by n minus 2. So now we have another one of these degrees of freedom types of problems. When we did standard deviation, we divided by n minus 1. Well, the reason we're dividing by n minus 2, first of all, the easy answer is it's beyond the scope of this course. But we only have n minus 2 degrees of freedom. Basically, whenever we have 2 points, those 2 points determine the actual line. We basically need to estimate our slope and our y-intercept. So 2 points determine the slope and the y-intercept. And then every extra point after that kind of gives us another degree of freedom. That's not quite exactly right, but that's kind of good enough. Basically, though, we're going to divide by n minus 2 in this case. And then we take the square root to get back into our normal y units of measure. So that's it. This value gives the approximate size of a typical prediction error. So we're going to kind of focus, in AP statistics, we focus on the interpretation of it. So how do we interpret the standard deviation of the residuals? Well, the standard deviation of the residuals in that sprint versus long jump example, when we were predicting long jump distances based off of sprint times, the R value was 22.4 inches. So we would say when we're using a linear model with sprint time to predict long jump distance, our predictions will typically be off by 22.4 inches, or our jump length predictions will be off by 22.4 inches. So that's how we interpret it. That's the most important thing. However, let's talk a little bit about how we can use our calculator to get it. Now on the AP test, usually they'll just give this to you, like in a computer output, which we'll talk about later. But I do expect you guys to get it from your calculator. So I kind of have two methods. One method is kind of doing it by hand, use the formula. And then the second method is to use this specialized function, which we haven't talked about, and we're not going to talk about to the very end of the year. But it's the easiest way to get it. So if you just kind of remember this function, we can get that value pretty easy. So let me show you that one first, and then I'll show you how to do it by hand. So if we have our data set here, first of all, we should look at the data set. Let's look at sprint time versus jump distance. We should observe that it is in fact linear. You could run the linear model if you wanted to see it, but unfortunately, when you run that analysis, it doesn't store the S value in there. I wish it did. I don't know why it doesn't. Well, I don't know why it doesn't, I guess. But if we look through our list, there's really not a stat s in there, unfortunately, which is why we need to use that special function. So let's go to Menu, go to Statistics, and then go down to these statistical tests. Now, we've not really run these before. This is where we're going to spend this whole second half of the year. But option A here says a linear regression t-test. So we're going to run that, even though we don't really know exactly what it is. Let's put in our x values, our x list, which is sprint. Let's put in our jump heights, jump distances. Then just leave these things alone. This is going to be for a later time. And go to OK. And it spits out some computer output. All kinds of crazy stuff. Notice the degrees of freedom. That's 10. That's the n minus 1. I think this set had 12 data points. I'm sorry, n minus 2. But here's the slope. Here's the y-intercept. And right here is your s value. That is the standard deviation of the residuals, 22.4. So that's the easiest way to get it, to use this unknown function. If you want to get it by hand, we could actually use the formula. Not that I would recommend it, but we could. All you need to do is square your residuals, divide by n minus 2, the degrees of freedom, and take the square root. So let's see if we have our residuals. Oops. So if we go to our vars key, we do have our stat residuals here. Okay, that's our residual list right there. Because I ran the linear model, those are our residuals. So basically what I need to do is I need to square all those, add them up, divide by the degrees of freedom, and take the square root. Divide by n minus 2. I could do that in one command on the calculator. You go to Menu, Statistics, List Math, and then you go to Sum the Elements. Or I could have just used the command sum. I could have typed in sum parenthesis, and then I want to take that residual list and simply square it. So what this command will do is it'll square all these residuals that you see here, and then it'll add them up. So that's the sum of the residuals. Then I need to take that sum, and I need to divide by the degrees of freedom. We need to figure out how many data, divide by n minus 2. I keep saying degrees of freedom, but it's the same thing. How many data points did we have? We had 12 data points. So 12 minus 2 is 10. Now that's in units squared, or in this case inches squared. Now I need to take the square root of that answer. If I take the square root of that answer, it gives me the 22.4. So that's kind of doing it using the formula and calculating it by hand. As you can see, I think this one is a little bit easier, which is why I favor it. Like I said, though, on the AP test, I don't even think you're going to ever have to really calculate that. But on my test, you do need to use your calculator to get it, so make sure you know how to get it. And then the second way to kind of talk about how accurate our errors are going to be, our prediction errors are going to be, is this new thing called the coefficient of determination. And it's kind of not new. For linear regression, if you find the correlation, if you just square that, it gives you what's called the coefficient of determination. For some reason, kids really have a hard time remembering what this means. Coefficient of determination, that's R squared. R squared is the coefficient of determination. Here's the formula for finding it. That's one way to find it. The other way for linear regression is just to find the correlation and square it. And here's the interpretation of it. Basically, it is the fraction of the variation in the values of y that is accounted for by the least squares regression line of y on x. Yikes. So what does that mean? Well, whenever, there's, like in our sprint versus jump height, there's a certain amount of variation in my jump heights. The linear model accounts for a certain percentage of that variation. If you recall this example, our R value was negative 0.848. So if I square that, it gives me 0.702. Also, if you go to vars, and it'll actually have an R squared variable, the coefficient of determination. So that's in there, but it is R squared. So that's 0.702. I have a rounding error here, sorry about that. So what does that mean? Well, this can be interpreted as a percentage. If you remember, like when our R value is negative 0.848, that doesn't really have any meaning other than describing the strength, describing the association, the strength of the association, the direction, and the fact that it's linear. So we never interpreted that actual number before. But when we square it, it actually converts it into a percentage that does have some meaning. Basically, when using a linear model with sprint time to predict the long jump distance, 70% or 70.2% of the variation in our long jump distances is explained by the linear model, meaning 29.8% of the variability in our long jump distances left over in the residuals. Okay, does that make any sense? Well, if it doesn't make any sense, that's kind of okay. This is how we interpret R squared. That's the most important thing in AP Stats. However, the next video I make, I am going to try to explain why this interpretation makes sense and why the formula is the way it is. So I would encourage you, kind of optionally, to watch the next video.